Thank you for joining us today. Welcome to Solving Manufacturing's 4 Big Challenges, an exclusive interview series hosted by Globalspec. The electronics design field is one of continuous change. Personal and industrial electronic devices are consistently being upgraded and redesigned to take advantage of new materials and components, new networks like 5G or the IoT, and also meet the increased functionality expectations from users. This can be a continuous challenge for those EEs charged with designing and testing the underlying circuits. In many cases, redesigning and testing a new integrated circuit before a device hits market isn't practical. Nevertheless, protecting these devices from electromagnetic and radio frequency interference is imperative. Thankfully, flexible solutions like electrically conductive tapes and other conformable materials exist. These technologies make it easy to offer new devices without circuit redesign. This saves product development time and resolves potential manufacturing bottlenecks. Joining me to discuss this is Jeff McCutcheon, Lead Technical Specialist for 3M. Jeff is responsible for 3M's EMI shielding, grounding, and absorbing solutions product line, and has been working in the electronics industry for more than 30 years. 3M brings decades of experience in EMI and RFI management and materials science to help engineers solve complex and dynamic design challenges. EMI and RFI solutions are known for boosting signal-to-noise ratios in consumer electronics to help improve signal integrity on 5G towers and even ground displays in automotive and connected products. Jeff, I'm really looking forward to our interview today.
And I'm glad to be here today too, Kevin. Thank you for the invitation.
All right, then. Well, without further ado, let's talk EMI and RFI solutions. Do you see a need for EMI and RFI management growing? And if so, what's driving that?
Yeah, Kevin, I do. And what I want to emphasize for those who are watching, there's 5 key drivers that are really driving what's going on in the industry. And so if you're an EE or a mechanical engineer and you're working on these systems, you may be familiar with traditional ways of producing grounding and shielding. Traditionally, it could be done with screws and clips, mechanical fasteners of some type, solder, and those would provide, grounding for many different types of applications. So when you think about product launches, for some of you, you watch product launches of, any new devices that are launched generation to generation. What's changing? And the things that you're going to hear that are changing are generally faster processors. The next thing you're going to hear is more antennas. You're going to hear that, they've gone from, again, from my era, from 1G to 2G to 3G, 4G, 5G, and now you hear about LTE, and then you hear these different aspects of different frequencies within 5G. You hear about the multiple gigahertz frequencies, the single gigahertz frequencies. All of those go along with the antennas, and you're all aware of the Wi-Fi and what goes on with the current Wi-Fi. And now coming out is the plans for future Wi-Fi 6 and 7, and NFC, near field communication, even wireless power has an antenna and can radiate RF type energy. And then improved displays. When you go back and again, when you look at the computers from 30, 40 years ago, it was the large tube displays. And then it went to the LCDs. And now it's going to the OLED displays. All of those displays require different types of grounding and EMI shielding. And there's always been challenges in each one of those generations as they change because the frequencies change. And when the frequencies change, generally you have a need for different grounding and shielding solutions. The other thing is the devices now are becoming thinner and more compact. Again, a lot of that has to do with the mobile handheld. Everybody has a laptop now that you carry around with them. You have, some type of a tablet or your phone, the computing power that's involved in there, and your ability to instantly connect with Wi-Fi and cellular towers and that is greatly improved. The other item to note is there's new circuit designs, new flex designs, and all of those all fit together. And so the key thing that you want to be aware of then is that faster processors mean that your EMI shielding requirements are going to be different and your grounding needs are going to be different. You're going to need hermetically, what we would call hermetically sealed EMI shielding and grounding. For those that have been in the industry for 20, 30 years, you can remember shield can lids that had holes in them to allow heat to rise and get out from the IC. Now, all of those shield can lids are sealed. They're completely hermetically sealed. And the question is, why is that? And the reason is because of high frequencies. The higher the frequencies, the EMI noise can escape. And if it escapes, it's going to be two issues for you. It's either going to interfere with another component within your device and create EMI noise within a system, or your device may not be FCC compliant. So it radiates emission outside of the device, and that radiation interferes with someone else's device. And so all of these devices have to be internally, or what people might call coexistence. They have to coexist within your internal environment, and then they have to exist with the environment that they're going to be sold into, so that my phone from my manufacturer doesn't interfere with your phone from a different manufacturer, or my phone doesn't interfere with your laptop's Wi-Fi, and those type of items. And so with that, then hopefully you see that there's those trends that we talk about. What problem then is this, hopefully the engineers who are listening are trying to solve? And so then, since we're aware of what we believe is the product roadmap going on in the industry, we try to anticipate what products are going to be suitable for helping to solve those problems. Both, these are conductive adhesives, conductive tapes, foil tapes, fabric tapes, EMI absorbers. What are the temperature requirements? What are the surface adhesion requirements? What are the long-term reliability requirements? What level of grounding and EMI shielding do you need given your frequency range, given your device? Hopefully that kind of gives you a good overview that we believe this is a tremendously growing market with lots of opportunities, and there's lots of opportunities because there's lots of challenges that need to be solved.
Thanks, Jeff. I think that was a really good overview of, the real big drivers behind the EMI and RFI shielding market. So what would you say are the types of products that most commonly need some type of EMI and or RFI management?
We would say now, historically, when you looked at products, it was mainly concerned about, are they meeting FCC requirements? And let's take hard disk drives, for example. They need to be FCC compliant so that they don't interfere with other components within a computer rack. But now when you get into consumer electronic devices that have antennas, now you're concerned about what we call signal to noise ratio. And what we want what's important to understand is that, for someone who's a layperson listening to this conversation, when you went from 2G to 3G to 4G to 5G, what you accomplished there is you could send a lot more data over a much shorter period of time. And so you could download videos, you could watch real-time things on your device. That wasn't available back in the 2000s. And because of the network, couldn't push the data bits and the data rates high enough. So about every 5 years, there's this floor shift based on the technology that's using about how quiet does your system need to be from an electronic standpoint so that your antennas can hear the signal that's being sent to them. Because the antennas are going to pick up anything within the frequency realm that they're targeted to pick up that energy, whether it's Bluetooth, Wi-Fi. Most of you now are aware of the 2.5 gigahertz and the 5 gigahertz frequencies associated with Wi-Fi. And you probably have that experience too, that you notice that some of them allow you different ranges. So the lower the frequency, generally the greater range and the greater stability of that, but it's a lower data rate. The higher data rates, you tend to need to be in closer proximity to the source, and you're more sensitive to interference. And so for the 5G devices, that are coming out, you'll see that they always have a backup. It's never just 5G all by itself. It's 5G with 4G LTE. And when 4G came out, it was always with 3G. And so as they're working out all the bugs in their systems, getting enough external antennas, cell towers, and all of those items set up, you need to be closer to a 5G tower than you need to be to a 4G tower. You need to be closer to a 4G tower than you do need to be to a 3G tower. So as that system was being developed, you would always have a few different frequency ranges that you could receive based on the signal to noise ratio. So your devices today, and the signal to noise ratio is important from a data error rate standpoint. So why is signal to noise ratio important? Is because of your ability to have high confidence in the data that you're receiving from a signal integrity standpoint. Because if there's errors in that data, or your computer or your device isn't quite sure if it's a 1 or a 0, you will get errors in your data. And for video, what that means is you start to see the video break up and it becomes staticky. And if it's a cell signal, if it can't get all of the information, you get a dropped call because it can't reliably communicate that. So you're going to get a dropped call. And so, so based on the devices in that, we see that all of the newer devices that are coming out in what we consider as typical now, a lot of people have grown up with it, is that all of the stuff going on in the background is trying to ensure data integrity. And so any system now that has antennas, and what you want to consider is, think about what has antennas now that didn't have antennas 10 years ago. Air conditioners, thermostats, refrigerators. And so now those devices need to have better grounding and EMI shielding than they had historically. Otherwise, they can have what we call interference. And if you go back, one of the fun things to do is to go on the internet and look up EMI, RFI interference problems. And you'll find out that back in the years, and even today, it would pick up that signal, and the signal for that stove said, oh, I'm supposed to turn on high the oven, and it would. Another thing that people want to be aware of is medical equipment.
So let me ask you a question then. How do engineers understand which EMI or RFI solution is best for their application?
So 3M has been making conductive adhesives and, conductive foil tapes for 50 years, going back to the, 50s actually. And so what's changed? And so the thing that's changed is better grounding, more reliable grounding, better EMI shielding, hermetic EMI shielding, all of these things that are needed now because of the higher frequencies. And so copper foil tapes are still copper foil tapes, but now the conductive adhesives that with that copper foil tape is much improved, significantly better in terms of grounding and shielding and operating at higher frequencies. And so based on what the customer is dealing with, and some of the terms that the industry will use is capacitive coupling, conductive coupling, inductive coupling, RF interference, based on what specifically the customer is dealing with, there's three basic solutions. There's the conductive adhesives that allow you to improve grounding. Now, you might say I'm grounding with screws or clips or things like that. The issue with those is there's always a gap, and you're not fully hermetically sealed based on the frequencies that you're going to be moving into. So we've seen numerous applications where customers will have a certain design that they've used successfully for multiple years, then they simply change some of the electronics within the package, and they're no longer FCC compliant. And they're trying to understand why. And the reason is because at the higher frequencies, the gaps that are associated with their grounding solution is not sufficient to keep all of that EMI energy within the device. So they're no longer FCC compliant. And so now their choice is either add a lot more screws or solder to completely hermetically seal it, or now you can use the conductive adhesives, which are basically different resins that have conductive members or particles, fabrics and foams within them, conductive fibers of various designs, depending on what the application is, to allow you to bridge the two surfaces together that need to be grounded, and so that you don't let EMI pass through what we call a bond line gap. The other thing that you can do within a cavity or whatever is look at EMI absorbers. And so the analogy that I like to use is we're all familiar with acoustics. All of us right now are in some type of a room. The room I'm in has a door, it has carpeting, keeps my voice within this room, and prevents noise from outside the room from coming in. Now, we're all familiar with doors that have a large gap at the bottom. The larger the gap, the more ineffective that door is at keeping noise out. So a lot of times you might put a towel or something to block if you have a large gap at the bottom of your door to keep noise out. So in both of these things, what we want to address is how hard is it to communicate acoustically? If a door is open and it's very noisy outside, it's hard within that room to communicate acoustically.
That's a perfect segue. So then what types of EMI or RFI management solutions does 3M offer?
So we have some basic categories. So when you think of clips and screws, they're holding things together and they're providing grounding. So now we have the conductive adhesives, which are adhesive on both sides. Many people are familiar that 3M has many industrial adhesives, electronics adhesives. So basically, we're taking a number of those chemistries and we are introducing conductive items. It can be conductive metals, it can be plated materials, plated fabrics, plated nonwovens that make them electrically conductive. And then they can be electrically conductive to different, different degrees based on what your application is. We've done a lot of research and development on optimized conductive fillers and also what are the resins that are going to go with those fillers. In some of the applications now, what you're finding is that the resin itself can be a contributor to some of the high frequency response. And so some of the engineers who are listening to this, who are dealing with high frequency applications right now, they know that the plastics that they use can interfere with the signal that's being transmitted. Will it transmit through the signal? And if it does transmit through the signal, how much signal is lost going through a particular type of plastic? And so at lower frequencies, that was never a problem because all the low frequencies pass through basically all plastics. At high frequencies, you start to get into some questions about what are the dielectric properties of the plastic. And so now we start to look at, for the conductive adhesives, not only are we optimizing the conductive fillers. So again, we look at what are the metals that are used. You can use silver, you can use gold, you can use copper, nickel, particles. They can be graphite, they can be metal-coated graphites, they can be metal-coated glass. All of these have plus and minuses to how they're going to perform. And there's some characteristics now that the industry is concerned about at the high frequencies that they weren't concerned about with 3G. When they moved to 4G and 5G, there's characteristics and also how they're designing the antennas so that they can send and receive signals at the same time. And when they do that, they can get some items that people may not be familiar with, but passive intermodulation, PIM, harmonics, those are becoming more of a problem because they become a EMI noise for your system or for another component that is within your environment that you're operating in. So the testing of these materials has become much more sophisticated. And so how we qualify our products now, we will actually do PIM and harmonics testing on our tapes so that we're designing them now, not just for contact resistance. If you went back 10, 15 years ago, what value do you find in data pages? You find contact resistance, and then everybody reports it on gold. Why? Because then your values always look good. But no one in the real world is building with gold because it's too expensive. They're building with substrates that are aluminum, stainless steel, and titanium, or variations of that. So, well, what's your contact resistance to stainless steel and titanium and aluminum? Very different than gold. And so we will, for the conductive adhesives then, we will design those conductive adhesives. Everybody has a different gap size now, from thin to thick. They have different substrates, whether it's aluminum, stainless steel, titanium, whatever it might be. And we want to provide grounding to it. And then do you need hermetically sealed or do you just need occasional grounding? Is it a shield can lid? Is an application potential within a device, but you've got EMI shielding out and around it also. So the conductive adhesives provide that grounding. The foil tapes and the conductive fabric tapes view that as the door. It's for sealing and also for grounding certain, within a lot of devices now, you have different levels of that device. And there are times that you need what we would call a grounding tab for floor 1 to floor 2 to floor 3. And so you introduce new grounding tabs. And so for the RF or the electrical engineers, you're trying to control the flowing currents within a device. All of your metal within your device is going to act like an antenna. And so all of your metal components within your device, you want to ground them together so that you have a neutral bias device. We don't want flowing currents. Ideally, that's what you want, but that's not what you're going to get. All devices are going to have some random flowing currents within your device. So you want to direct them in a certain direction, away from your antennas. The closer they are to your antennas, the more EMI noise it'll make. So envision, for the folks that aren't familiar with that, you can have random currents flowing through metals within your device. It's like little rivers. And you don't want those rivers to go next to your little towns, which happen to be your RF antennas. So you want to redirect them. So you build little dams so they flow in different directions to get to your overall ground plane of your device. And so if you can route them away from your antennas, if you can route the flowing currents that you know are going to be occurring away from your antennas, you're going to have a quieter RFI device for your antennas so that they can operate more effectively with better signal-to-noise ratios. And those signal-to-noise ratios will improve your error rates so that you have a very reliable device, a very reliable communication device at all of these different frequencies. So we've got the conductive adhesives for grounding, hermetically sealing. You've got the conductive foil and fabric tapes to be your doors, to close off systems or to reroute, flowing electrons. And then you've got your EMI absorbers that, again, we associated with like acoustic tiles. That's when you've routed everything where it needs to go and your system is still a little noisy. You just want to quiet the room that you're operating in within that system. Then you put in EMI absorbers, and they will, pick up directly on top of the device. They'll, absorb it coming out of the device, or you can put it on a reflecting surface. If you're not able to fit it right where it needs to go, then EMI absorbers would generally go onto a reflecting surface or over a component like a flex circuit. A lot of absorbers are placed onto flex circuits to protect them from stray EMI noise. It can get onto the flex circuit and interfere with the signal that's going down the flex lines.
So when it comes to the actual device manufacturing, how would a manufacturer go about integrating one of these solutions into their production line?
So generally, historically, some of these products were considered Band-Aids, where they were designed in after it had the device was along a certain path that it was hard. You didn't want to redesign the product because that would delay your launch schedule by months or years. And so you wanted to do an incorporation of these products as best you could within a design. And then a lot of people would just simply learn from that past design that was so arduous that, okay, we're going to start designing in from the very beginning. And so I would say most common applications now, there's a discussion that begins at the very initial prototyping, where as you go through your prototyping stage, you're going to try a couple different variations and versions of your product, where you begin to incorporate these materials into the design, because you're recognizing if you start to become familiar with the math, you can understand, what are your gaps, what are the frequencies, how close are my components going to be together, and you can start to look at it and go, okay, I'm likely to have an RF problem or an EMI problem. I'm going to have some stray EMI noise that could leak, or it's might interfere with this other component. I've got a flex circuit that's going to have to be routed very, very close to this processor. I'm going to probably have to put some additional shielding on it. And So you anticipate that ahead of time. So if you anticipate it from the beginning or have some of those conversations ahead of time, then you can design it in. And what a lot of people will do in their initial builds is they'll mock up a couple different designs.
Jeff, you are just a wealth of shielding knowledge, and I want to thank you for taking some time to share that with our audience today.
It's been great. And I know there's a lot more that we could be talking about. And so we just encourage people to look at, our websites and to inquire about some of the products. And we just look forward to, what the opportunities might be.
To our viewers, thanks for watching. Join us for the next episode of Solving Manufacturing's 4 Big Challenges, hosted by Globalspec.